I'm Ethan Kwan, and today we're going to be talking about what is the largest star in the universe, and what is a star anyway. So to answer the first question, we're going to have to first answer the second question. What is a star? Now, to start this video, we're going to be talking about failed stars, or things that would want to be stars. Things that would want to be stars. Okay, so to start, let's look at our planet Earth. Not to learn anything, just to get a sense of view. So let's zoom out, and we get to the planet Jupiter, the biggest planet in our solar system. It is about 11 times Earth's radius and 317 times its mass. Yes. So, and it is basically made up of the same things as our sun, about 70% hydrogen and 27% helium. So, let's get rid of that. And, okay, so let's go a little bit bigger, and we get to brown dwarfs. A brown dwarf is a failed star that are huge disappointments to scientists and scientists. Brown dwarfs are about 30 to 90 times Jupiter's mass. So, that means that if we slam 90 Jupiters together, even though that'd be fun to watch, we still wouldn't get a star. We would get what is called a brown dwarf. Interestingly, adding mass to a brown dwarf pulls the outer layers in because there's more gravity, and it will make it smaller. So if you throw more Jupiters, it will probably get smaller. Okay, but we don't really want to talk about failed stars or failed wannabe stars. We want to talk about actual stars. Okay, so let's begin our discussion about stars. Main sequence stars. So a main sequence star is when a brown dwarf gets enough mass to do this what's called the proton-proton chain, where it smashes hydrogen into hydrogen, producing helium. Or here's one of the steps. You smash these into each other, you nuclear fusion, and we get 2 protons and a helium atom. Okay, so if you increase the mass of a main sequence star, it will get a lot brighter, like really bright. Here is the life cycle of a main sequence star. Birth, and then most of its life, it's in its main sequence stage. These stars are kind of like our star, our sun, right? This is how, and there's a giant phase, and then there's death, right? Okay, so just remember here that some of these stars are going to be really young, and some of them are going to be ending their lives. So we're talking about size is kind of relative because it could be like a baby to an adult. There's a big difference there. So just remember that as we go on. Now let's talk about the first real stars. Red dwarfs. They're about 100 times more massive than Jupiter, and these are the stars that don't really do much once they die. They just kind of fizzle out and get smaller and shrink into a white dwarf. Just a core, right? Okay. Red dwarfs are by far the most abundant type in the galaxy, and these last for the longest as well. If the little green section is where we are now, this is how long they would live. So, these stars are really, they live a long time, which is an understatement. Okay, so this is about how big it is, and well, so here's a star called Barnard's star. It is a red dwarf about 6 light years away, and it's also getting closer as we speak. Yes, it's coming toward the solar system. We don't really want to talk about these stars because they're kind of boring. Let's talk about actual stars. Let's talk about the yellow stars, like our sun. Okay? So, here's our sun, and to say that the sun dominates the solar system is an understatement. Because the sun makes up about 99.86% of the solar system. here it is, right? So it is about 2 times the temperature of Barnard's star, and it will only live for about 10 billion years because of that temperature change. It is about 7 times more massive than Barnard's star, but because of that, it's about 300 times brighter. Okay, now, let's go bigger. Let's go bigger. Let's literally go bigger. That's not bigger. Okay, so, if you change the mass of a main sequence star, it will make many drastic changes to its color and its temperature and its color. Yes. So let's talk about one of the brightest stars in the galaxy. It's called Sirius, and in this case, it's not. It's only about 1.7 times more massive than the sun. Okay, so that's Sirius. Let's now talk about Beta Centauri. It's about 10 times the mass of the sun, and it's a group of 2 stars, not just one. Each one has about the surface temperature of 2,500 degrees Celsius. Okay, and okay, so this is about how big it is, which is it's pretty big, which is an understatement as well. It's really big. So Beta Centauri is about 25,000 degrees Celsius, and because of that, it will shorten its lifespan to about 20 million years. Mass is about 10 solar masses, or 10 times the mass of the sun, and that makes it almost 20,000 times brighter than our sun. Okay, so is this the formula? More mass equals bigger star and brighter star? Well, let's talk about one of the brightest stars or one of the most massive stars in the galaxy. It's called R136A1, which is a very uncreative name, and this is why scientists are so bad at naming things. So, the mass of R136A1 is about 315 solar masses, or 315 times the mass of the sun, and this makes it about 9 million times brighter than our sun. It's about 30 times the radius of the sun, and since it's so big and bright, it will last only about 1 to 4 million years. So this is about how big it is. Okay, that's actually pretty big. Okay, so R136A1. R136A1 is let's see, what's the right word? Dramatic, extreme, that it loses about 321,000 tons of material every single second. That's actually really amazing. Okay, so there's a problem with R136A1. It kind of breaks the rules of star formation a little bit, because the mass limit is about 150 times the mass of the sun. If it's bigger than that, it will probably blow away any other material. With its solar wind, it would probably blow away any other material to make it grow bigger. So this means that R136A1 was probably formed by the merger of many other stars in like a really close star cluster group. So here's R136A1, and it's very big, so it's only going to live about 1 to 4 million years. Okay. Okay. So from here, it's not that you have to make more mass or add more mass to make it bigger. From now, it would making it bigger would not really work. To make the biggest stars, you have to kill them. That wasn't a very good animation, but okay. Anyway, let's talk about the biggest stars, red giants. So once a star, like the sun, has entered the last stage of its life, it expands because the core isn't producing as much energy as it's supposed to. So the core is under immense pressure from all the other star that's on top of it. It's pushing against it. The only thing that keeps it up and not collapse into a black hole or whatever it is, right? Neutron star, whatever, um, is the pressure that's coming out of the core and because of the nuclear fusion and just pushing out the layers, and it's in balance, right? When a star uh, dies, it will, let's just take a cutaway here, it will contract a little, okay? So, and that will make the core get smaller, which means the core will get hotter. And if a core gets hotter, that means it will fuse bigger and bigger elements together. So that means it will produce a lot of fusion energy, which means the star will expand, like our sun, or what's called gamma crucis, or Gacrox for short. So here's our diagram again. Let's go to Gacrox. Gacrox is about this big, and if you think that's impressive, let's look at our sun in the future. Our Gacrox is about 84 times, it's about 84 times the sun's radius, even though it's only about 1.3 times the mass of the sun. And if you think that's impressive, let's look at the future sun, how it will expand in its future, literally. So this is how big the sun will be one day, and it will pretty much swallow up Mercury and Venus and make living on Earth very uncomfortable. Now, that burning up wouldn't really happen because A, there's no oxygen, and B, it doesn't really work that way. So let's just move on. So let's move on to the largest stars that there are. If you think that's impressive, let's move on to the largest stars that there are. Hypergiants. So here is our diagram again. Now, let's go to one of the biggest stars in the, not the biggest, one of the bigger ones. Okay, so what is one of the bigger ones? It's called Pistol Star. Pistol Star, and as you can see, there's our sun, has a little dot there. So, Pistol Star is only about 25 solar masses, but about 300 times the radius of the sun, which is a lot. Okay, and if you think that's big, let's go to the bigger stars. This is a blue hypergiant. Let's go to a bigger type of star called a yellow hypergiant. The most well-studied yellow hypergiant is called Rho Cassiopeiae. Rho Cassiopeiae is a star so bright that it can basically be seen with the naked eye even though it's thousands of light years away. At 40 solar masses, this star is about 500. At 40 solar masses, it is about 500 times the radius of the sun, and is about 5,000 times brighter. 500,000 times brighter. If we accidentally magically transported Rho Cassiopeiae to the sun's location right now, Earth would be inside and you would be very dead. Also, these two planets would probably be burned up as well. Anyway, yellow hypergiants are very rare though. Only about 15 are known. Now, let's get to the biggest stars of all, red hypergiants. Now, so who wins this contest for the biggest star? Well, the truth is, we have no idea. The problem is, red hypergiants are so far away that tiny changes in our measurements could lead to vast changes in size, right? So it's kind of hard to figure out the biggest, and it's kind of hard to put a title on one because we could find a bigger one. But let's talk about the 3 biggest stars in the galaxy that we know of course. Okay, so in third place is VY Canis Majoris. Now, this star is about 17 solar masses, which isn't that much actually, compared to Rho Cassiopeiae, which is about 25 solar masses, 40 solar masses. Sorry about that. But it is about 1,400 times the radius of the Sun. 1,420 times the radius of the Sun, to be exact. Okay, so second place. UY Scooty. Like, what kind of name is that? Like, it's so cute, but it's so big. So, I mean, that's kind of odd. Okay, so in second place is UY Scooty. I have to laugh. So, at 10 solar masses, which is smaller than VY Canis Majoris, it is 1,708 solar radii. Now, to get to the biggest star that we know, we are going to have to go much bigger than this. Okay, so the biggest star that we know of currently is called Stephenson 218. It is at 15 solar masses, but it is about 2,000. It is 15 solar masses, but it is about 2,150 solar radii. Okay, so let's make this journey again, but without the talking. So, the universe is a big place, and we might not be able to go that many places. If you got a sense of small, good. That's kind of what I was aiming for. Okay. So, I won't talk anymore. I'll just let you watch this. Yes, so we are pretty small. Okay, so, and we are going to give a medal to Stephenson 218, even though this would probably not fit. so, thank you so much for watching. If you like this video, please hit the thumbs up button, subscribe, and share this video with other people or your friends. Also, click the bell so you won't miss any videos. See you at howtodostuffwithethan.com. I'm faster than typing. And see you next time. Bye.